In this section, we would like to present the seismic analysis of a quite simple 4-story reinforced concrete office building using the Eurocode standard. The main dimensions are 25 meters times 25 meters. The height of each story is 3 meters. We have a bottom slab with 50 cm and slabs with 30 cm thickness. The main beams are 20 x 80 rectangle profiles. We have circular columns with 35 cm diameter in the corners and rectangular 20 x 40 columns at the edges. The main load-bearing part of the structure is the core, with 20 cm thick walls and 6.8 meter x 6.8 meter outer dimensions. The concrete grade is C25/30. The reinforcement is S500B or C. The bottom slab and the slabs are modeled with shell elements. The columns are beam elements with hinges at the bottom and at the top, while rib elements are used for the integrated beams. The building is supported by a bottom slab, so surface support is used to model the soil stiffness. The dynamic spring stiffness is 100,000 kN per square meter per meter in the vertical and 10,000 kN per square meter per meter in the horizontal direction. It is important to use the dynamic stiffness of the foundation if you want to carry out a seismic analysis. Now let's check out the loads. In this example, we focus only on the seismic analysis, therefore we do not have wind, snow or other loads, we have only permanent and imposed loads. The structure weight is calculated automatically by the software. Additional permanent loads are considered with a 3 kN per square meter surface load. Office buildings have an imposed load category B, so we define a floor load of 3 kN per square meter. For seismic analysis, we need only the permanent part of the imposed loads. We create a combination accordingly, and we use a combination factor of 0.3 for the imposed loads. This combination will be used for the vibration analysis. We will use mesh only for the shell and rib elements, using an average mesh size of 1 meter. If we divided the columns, we would get their local vibration modes as well, which have a low contribution to the global behavior. Due to their stiffness and hinges, the columns will carry only an insignificant amount of the seismic loads, therefore they are not relevant regarding the global seismic behavior. With this trick, we can avoid using hundreds of vibration modes for the analysis, and we can save a significant amount of processing time. Now, we go to the vibration module and set the parameters for the vibration analysis. We will use our predefined combination for the analysis. The required number of mode shapes is 10. We will use the default values for the convergence criteria. Since the structure consists of reinforced concrete elements, we can expect cracks and stiffness reduction during an earthquake. In case of beams and columns, we can define a reduction of 0.5 for all components except for the normal stiffness. For walls, all components can be set to 0.5, and for slabs, only the normal stiffness should remain 1. Converting slabs to diaphragms greatly speeds up the calculation. Whether the slab actually acts as a diaphragm can be checked by a simple deformation test of the slab according to Eurocode. If we calculate the slab as a real deformable shell, we never make a mistake with it, but we have to take into account the higher computational capacity and time. For buildings, except for some unusual cases, it is sufficient to consider the masses in the x and y directions. One of the very useful features of the program is its ability to ignore masses below a certain height. This is really helpful typically for structure parts like base plates and other foundations in the ground, as these structural elements behave very rigidly, their mass cannot be moved, contributing little to each vibration mode. As a result, even with the consideration of hundreds of vibration modes, in some cases we cannot reach the 90% effective model mass required by the standard. Special rules apply to structures that move rigidly with the ground, but as long as their mass doesn't affect the resulting stresses, as in our case, they can be removed from the mass matrix. In this example, we want to ignore the weight of the base plate. The base plate is located at a height of minus 0.25 meter, so only masses above minus 0.24 meter will be considered in the vibration analysis. Now we can carry out the vibration analysis. Our first shape is a torsional shape. The second is the Y direction. And the third is the X direction oscillation. We can check also the other vibration modes. Note that we didn't obtain any local vibration of the columns, since we didn't assign mesh to these elements. The structure is medium soft. The first vibration mode can be characterized by the natural period of about 0.6 seconds. Now let's look at the tabulated results. We go to the effective model mass table and check if the 90% requirement of the standard is met. Apparently yes, so we can move on to defining earthquake loads. We go back to the load module and we define our seismic load. Since we already have the vibration results, we can set the parameters for the seismic spectrum and for the seismic analysis. First, we set the parameters of the spectrum. The importance factor is 1. We use a limited ductility design, so we apply a behavior factor of 1.5. We use type 2 spectrum with a ground type of C and a peak ground acceleration of 1 meter per square second. We don't need a vertical spectrum, since its effect is negligible in our case. We leave the direction as default. We can define the stories of the building so that the program can automatically calculate the torsional effects, and after the analysis also the sensitivity coefficient for each story. We use the pickup function and we pick the different points of the stories. We apply torsional effects with a coefficient of 0.05 according to Eurocode and move on to the combination methods. It is always safe to use the CQC method for the model responses, and we will use the SRSS method for the direction combination for this example, assuming that there is a low cross-correlation between the directions. After defining the seismic loads, we can go to the Static Analysis tab and start the linear static analysis. After the analysis, we get a warning message. The program let us know that we use a stiffness modification, and this can have an effect on the normal loads that require the unchanged stiffness of the members. Basically, it means that we have to carry out the analysis and design in ULS and SLS using a separate non-change model. Before we check the results, we can display the center of gravity and shear center of each story for better understanding of the seismic behavior. We go to the display options and check these two boxes. The black symbols are the centers of gravity, while the red symbols are the shear centers of the stories. Right now, we can switch them off for a better overview. Now, let's see the results. We select the ULS seismic combination. The software automatically calculates the load combinations defined by the use standard, in our case Eurocode. In this combination, the seismic loads are already combined for each vibration mode and seismic direction, and then the permanent loads and the quasi-permanent part of the imposed loads are also added. We can check the displacements of the structure, but of course the program can show the beam internal forces, stresses, hinge deformations, surface internal forces and stresses and strains, reaction forces, and so on. These can be used and imported into the different design modules for further analysis and standard design checks. In case of a complex model, it is not easy to understand or check the global results. Using a virtual beam and axis can help us to present the global internal forces integrated on the selected structure elements. We know that the main load-carrying element is the core of the building. If we select it and define a virtual beam for the surface elements of the core, we can easily check the global results. So let's select the virtual beam icon and define a new virtual beam. We name it core, and then we select the required surface elements of the core. We already created a user-defined view to accelerate the process. There are different options for the axis of reduction. We use a straight line for our example. We can check the global normal force of the core, which comes from the considered mass in the seismic combination. We can also check the integrated base shear forces, which are basically the total horizontal force acting on the building, since the columns have hinged ends. And also, we can display the global bending moments, which are useful for the assessment of the global behavior and for the estimation of the required wall thickness in a preliminary design phase. The virtual beam can display the results of any loads or load combinations, so with these global internal forces, we can also decide whether the seismic or the wind load is an authoritative horizontal load. If we click on the virtual beam, we can get the graphical results like in case of a normal beam. Now let's check the tabulated results and also the sensitivity of the building to second-order effects. The results, such as displacements, internal forces, stresses, reaction forces, can be seen here in a structured tabulated form, and they can be copied, exported, or added to the report. Let's move on to the seismic sensitivity of the stories. As we can see, the interstory drift sensitivity coefficient is always under 0.1, therefore second-order effects are negligible. They do not have to be considered. After the analysis is finalized, we can design the structural elements and carry out the standard checks using the RC, steel, timber, or masonry design modules of the software. For example, our reinforced concrete building could be completely designed with an automated procedure using the RC1 module for the slabs, RC2 for the columns and beams, RC3 for punching shear, RC5 for the core, and also RC6 to analyze the crack state of the structure elements. However, due to the limited time here, standard design and checks are out of scope of this webinar. Therefore, this is the end of our presentation, and of course, I would like to thank you for your attention.